Steve, is that even a word? Actually,
Okay, objectives for 2.6. We're looking at graphs of functions. Guys, most of this is a review. Okay? We're going to look at something called continuity.
Oh.
Okay?
I thought it was like continuing.
Continuity. Continuity is from the word continuous. So something that's continuous, you can draw without picking up your pencil. Okay? We're going to talk about a lot of different basic functions. The identity function. Recall the identity function is y equals x. What's the squaring function?
The square.
Y equals
X squared.
x squared.
Oh.
The cubing function.
Y equals X cubed.
Y equals x cubed. What does the line y equals x look like? Cell number 2.
Great.
Okay.
Oh, I was gonna put the
Y equals x looks like that, right? What does y equals x squared look like?
Is it a graph?
A parabola with the vertex at the origin. Nothing new, right? What does y equals x cubed look like? Yes. Looks like this. Okay. The square root function, that would be y equals
The square root
the
of
square root of
X.
x. What's that one look like?
Cute. Is that the one that has a?
Okay, yes. Okay, the square root is the one that looks like that. Okay. Cube root function, that would be y equals what? The cubed root of x. Anybody remember what the cube root function looks like?
Wait, so it is like that?
It kind of looks like the cube function, but it's here.
That's what I did. Go with me.
Okay? The absolute value function, y equals
The big lines and then X in the middle.
absolute value of x. What does that one look like?
A V.
A v. Okay? Any of that new?
No.
No. There's a couple more we're going to look at. Number 5 is a piecewise defined function. You remember what a piecewise defined function is? Okay, there's some breaks in it. Why? Separate, right? Piecewise. Multiple pieces, right? I'm going to take some pieces of functions and put them together and make it one. A piecewise function. A function that's not listed up there that we'll also talk about was the greatest integer function. And that's the one that looked like steps. And then number 6. So everything above number 6 talks about functions. And then you get to number 6 and it says the relation. Why do you think number 6 says the relation x equals y squared?
Why is that a function of X?
Because it's not a function. That's why. Okay? If I was going to graph x equals y squared, it looks like this. Is that a function?
No.
And it clearly fails the vertical line test, right? Okay. So it's a relation. And that is what we're talking about in 2.6. So the first 5 or 6 slides we're going to look at, I'm just going to talk about each function, give some general properties of it. You'll probably just want to do a screenshot. Okay? First off, we have, definition of continuity. This is not the mathematical definition. This is a generic. A function is continuous if you can draw it without picking up your pencil. If you have to pick up your pencil, it's discontinuous if that's fine. Okay? A function can be continuous in a set domain, and then discontinuous, and then continuous again. Okay? And let's talk about that one first. Describe the intervals of continuity. What this question's asking is, looking at these graphs, where are these graphs continuous? Or are they not continuous? Graph A, what does that look like? It looks like a function. Huh?
X squared.
Looks like x squared, looks like a parabola. Okay? Do you see any breaks in graph A?
No.
No. So reading from left to right, where did it start? Negative infinity. Where does it end?
Positive.
Positive infinity, with no breaks. Right? I could, theoretically, I wouldn't, because it'd be the last thing I do in my life, draw this without picking up my pencil. Okay? So when is this thing continuous? It is continuous on the open interval, negative infinity to infinity. That graph is always continuous, correct? What?
You couldn't start it.
I know. Graph B. Is it continuous on the same interval?
No.
Why not?
So that stop.
It's got a hole in it. This line has a hole, and that's what we'll call it. We'll call them graphs, we'll call it with a hole. Okay? But even though this graph itself on the whole domain is not continuous, it is continuous on most parts of it, right? When is graph B continuous?
-32, 3.
Okay, it's continuous on the open interval, negative infinity to 3.
Open interval U.
Okay, union, because it starts again at
3.
just after 3 going to. Okay. So even though the whole function is not continuous, because there is a discontinuity within it, it is continuous on those two intervals right there. Pretty simple? Pretty simple. Okay. Moving on. Identity function. The identity function is y equals x. The domain is all real numbers, from negative infinity to positive infinity. The range is all real numbers, from negative infinity to infinity. As you look at this graph from left to right, this graph is always increasing. So this graph is increasing on the entire domain, from negative infinity to infinity. Does this graph have any breaks in it? No breaks. This graph is continuous on the interval, negative infinity to infinity. Pretty straightforward. Why is it called the identity? Because you give me an x value, and I'm going to tell you the y value is the exact same thing. Whatever you input is what you output. What you put in is what you get out. You put in your identity, you get out your identity. Okay? Next graph. Y equals x squared, called the squaring function. The domain, x can be anything. So the domain is from negative infinity to positive infinity. The range, oh, it can't be everything, can it? Because a parabola has a low point or a high point, but the parent function has a low point. The lowest it can go is 0. And from there it goes to infinity. So the range is from closed interval 0 up to open interval infinity. As you're looking at this graph, as we start at negative infinity, as we come towards 0, this graph is getting lower and lower and lower. So this graph is decreasing on the interval negative infinity to 0. What happens at 0? It begins to increase. So it's decreasing from negative infinity to 0, and it's increasing from 0 to infinity. It is continuous on the entire domain. Folks, that's the squaring function. Next function, the cubing function. On the cubing function, x can be anything, so the domain is all real numbers. The range can also be anything, so the range is all real numbers. As we read from left to right, this graph is always increasing. So this function is increasing on the entire domain. There are no holes, there is no discontinuity, therefore it's continuous on the entire domain. And that's the cubing function. Questions or anything on so far? The next function is the square root function. The square root function domain is not all real numbers. Why not?
It's domain and range stop at 0.
Why does the domain start at 0?
Because it doesn't go below.
Why?
Well, that's not a question.
Because you cannot take the square root of a negative number, right? Because the square root of a negative number is imaginary. The square root of a negative number is imaginary. That's why the domain is 0 and greater. Well, the smallest possible value for the domain is 0. And the square root of 0 is 0. And what happens as x gets bigger and bigger and bigger? What's the square root of an extremely large number? But it's still going to be big, right? So it's going to get bigger and bigger and bigger. That's why the domain and the range of the squaring function is 0 to infinity. It is continuous on the entire domain, but the domain is only from 0 to infinity. And this graph increases, right? Always. It's always increasing from 0 to infinity. Notice every one of these start at 0. I'll also point out on the increasing part, you're going to see textbooks argue on this factor right here. Okay, they say this book says it's increasing on the open interval 0 to infinity. Some books say it's increasing from closed 0 to infinity because that's a starting point.
Online did that too. I missed it.
It's very inconsistent, and I hate it. Okay? But what you do want to pay attention to is how's the question asked. If the question asks you about the open interval, you better not use brackets. If it's flat out saying, what is the open interval, then it's going to be parentheses. Okay? Questions on the square root function. Okay? Cube root function. Domain is all real. Range is all real. It's increasing forever. It's continuous forever. No breaks. Questions on cube root function. Absolute value function has a lot of properties just like the squaring function. Domain is all real. Range is 0 and up. It's decreasing from negative infinity to 0 and increasing from 0 to infinity. Continuous on the entire domain. Sometimes the absolute value function is represented as a piecewise function. Because if you look at the graph of the absolute value function, everything to the left of the y-axis just looks like the line y equals negative x. And as soon as you hit 0, the graph looks like y equals x. So you can actually call the absolute value function a piecewise function and define it with two separate lines. Okay? Questions on absolute value? Told you we're going through a bunch of stuff today. Okay? All right, let's graph it piecewise. Y'all remember doing these last semester? Okay. We did do them, Hannah, I promise. I have two piecewise functions. Here's the first one. I'm going to walk you through how I graph this. And then after this one, you're going to graph one by yourself. let's say I wanted to graph the line y equals negative 2x plus 5. I'm just going to graph that line. No big deal, right? If you were to graph the line y equals negative 2x plus 5, what would you do? Start at 5 on the y-axis. Why?
Y-intercept.
Because that's my wire.
That's your what?
Y-intercept.
Y-intercept. From that y-intercept, what would you do?
Your slope.
The slope. In this case, the slope is
Negative 2.
-2, which means
Negative 2 over 1.
down 2 over 1, down 2 over 1, and so on. And then you can reverse it, go up 2, back 1, right? After you plot your points, you would draw your line. And don't be jealous if your lines are terrible. I'm an expert at this. In my own mind. Any curve in that line is not the drawing, it's your mind that's warped. Okay, folks, that is the line y equals negative 2x plus 5. Is that what I'm supposed to be graphing though?
No.
I'm graphing that line, but there's a stipulation. This line only exists when x is less than or equal to 2. So what happens when I get greater than 2? What happens to that line? It disappears. So this line only goes to an x value of 2. Right? Unless, that way. So everything to the right of that point needs to go away. That is the first part of this piecewise function. The second part, if I was going to graph the line with an eraser, y equals x plus 1, how would you graph that?
Start at 1 and then just
Start at 1,
straight.
up 1 over 1, up 1 over 1, and so on. And you would draw that nice straight line, right? But that's not what this line is. That's only as soon as we pass 2. Right? So if we started here at 1, up 1 over 1, up 1 over 1, this graph is going to start as soon as we pass that point. From there, that line exists. Is that a function?
Yes.
Yes. Is it continuous?
No.
It is continuous on 2 separate areas, but the whole graph itself is not continuous, right? If this was a closed circle, we got a problem.
It's not a function.
Then it's not a function, it fails the vertical line test, right? Are there any questions on how we graph this?
Wait, so how is it not a function?
It is a
Like,
function.
how is it a function?
For every x value, there's only one y.
But those points are like,
It's not shaded in, so it's not equal to.
That's a closed circle, that's an open circle. So at 2, we're going to use the blue function.
Yeah.
Okay, if I was going to graph the line 2x plus 3, I would start at 3. And that slope is 2. So it's going to be a steep line like this, right? Increasing. But this line only exists when x is less than or equal to 0. So I'm going to use that closed circle. And I'm going to go to the left. So down 2, back 1, down 2, back 1, down 2, back 1, and so on, like so. Terrible line. Okay? So that is the line 2x plus 3 when x is less than or equal to 0. Now we got this next graph. And I'm gonna talk you through it from the parent function. What is the parent function of negative x squared plus 3? X squared. What does y equal x squared look like?
It's like parabola.
Looks like this. Right?
Negative, it's
What's the negative do?
Plus it upside down.
Down here. What does the plus 3 do?
Make
Yeah,
it.
so go,
Brings it up,
shift it up.
right? But I only want that side of it, right? I want the side to the right
That's greater than 0.
because it's greater than 0. Okay, this is how I do this. I've taken the parent function y equals x squared and shifted it up 3 units. So pretend with me, if you will. I'm going to pretend that this open circle value right here is my origin. I'm just going to pretend that that's my origin. Okay? If I went right 1, what is 1 squared? 1, but I want the opposite of that, so negative 1. That point is going to be on my graph. I'm now going to go back to my pretend origin. If I went right 2, what is 2 squared?
4.
But I wanted to go the opposite direction, so from there, I'm going to count down 4. 1, 2, 3, 4. And for the heck of it, let's do one more. Go to my pretend origin. Over 3.
Be 9.
9, so
It's a negative 9.
1, 2, 3, 4, 5, 6, 7, 8, 9. Do my red dots form a parabola look?
Yes.
Okay? So it's kind of went down like this, and then steeper, and then steeper, and so on. And folks, there's your piecewise function. Okay? Is this graph continuous from negative infinity to infinity?
No. Wait.
Yes,
Yes, it is. Yes, it is. Because the open circle and the closed circle happen to be at the exact same point. Okay? I have a closed circle on the blue line and an open circle on the red curve. So this is continuous from negative infinity to infinity. How do you feel about this? Santiago, you all right? You have a long weekend? You keep closing your eyes on. Did you work hard this weekend? Did you work this weekend? What do you do? Mechanic?
Do you know what you do?
What do you do? Do you do tile work, brick work?
He does fencing, yeah.
Fencing? Who? Digging post holes? That sucks. All right, any questions on this, guys? All right, next type of function is the greatest integer function.
Where it's like less than or greater than, or like when it says equal to, that's a closed, right?
The equal is closed.
Okay.
Yeah. The greatest integer function is often referred to as a step function, okay? So what's going on in the greatest integer function is I want the greatest integer based on the value I give you. So an example, if I said what is the greatest integer of 2.6, okay? Anytime you have a greatest integer, it's like a double bracket looking thing. If you see the double bracket, that means greatest integer. Sometimes it might look like a bold bracket. So be careful that you don't think the greatest integer is an absolute value or vice versa, okay? They're clearly different. So let's think about where 2.6 is on a number line. Where would you find 2.6 on a number line?
Right side.
Between what two numbers? Between 2 and 3. Is it quite 3 yet?
No.
But it's bigger than 2.
Yes.
Yes.
Okay, so the greatest integer of 2.6 is 2. That's what it is. and you give me any value between 2 until almost 3, and that greatest integer value is going to be 2. The greatest integer of 2.99999 is what?
It's 2.
It's 2, because it's not 3 yet,
But it's 2.999.
but it's
Yeah, but
not
it's not
3.
3.
I'm so confused.
Okay? It's not 3.
Okay.
And if you look at this graph, that's what it's showing. The second, I'm going to start on the positive side. The second we're at 0, 0 is an integer. And it's going to stay 0 until,
It gets
I guess the
1.
one.
as soon as you get to 1, boom, it changes. At 1, it goes up to 1. And it stays 1 until 2. And then it jumps up. Okay? What can x be on the greatest integer function? What's the domain? The domain can be anything. You can give me any value you want. And the ones that I really dislike are the negative numbers. What is the greatest integer of negative 3.4?
-3.
Oh,
So
actually,
it'll be -4.
It's
Oh
negative
my
4.
gosh.
It's
Why?
negative 4. Because negative 4 is over here, negative 3 is over here, and negative 4 is in the middle. So negative 4 is bigger. I'm sorry, negative 3.4 is bigger than negative 4, but it's not quite negative 3 yet.
That,
Okay, so and that's why I hate the greatest integer function. But it is what it is, guys. Okay?
I do not understand.
me either.
The range. Notice that y can't be just anything, can it?
Well, it can only be whole.
Y is only in integers, not whole numbers, because that disqualifies negatives.
Yeah.
Okay? So if you remember from the past, we might write that the domain, we might say that x is an element of the reals, right? Or negative infinity to infinity. There's actually a little shortcut thing you can write for integers. And it's not I. It's a Z. Okay? It's a double stick Z. So if you see a double stick Z, that implies integers.
Why is it not an I?
Because that refers to imaginary numbers.
what if it's capital I?
Should
Right.
be a double stick.
Why is it a Z?
It just is.
You should.
Well, wait, lowercase I is what, right, is relative to imaginary. Why can't it be a capital I since there's such a specialty between the two?
I just said capitalized for imaginary.
I thought it was lowercase.
It's the set, there's not really a set of them anyway. Yeah, I think rational numbers are Q with a double stick on the Q.
Why is math so confusing?
Okay.
It's so.
It's some weird stuff.
Math just decided to like expand its horizons from numbers.
Oh,
and script.
It's some weird word.
Letters.
Okay, so the greatest integer function on a whole is discontinuous, but it is continuous on some pieces of it, right? It is continuous from 0 to 1, and it's continuous from 1 to 2, and it's continuous from, does that make sense? So on these little bitty subintervals, it's continuous, but it's not continuous on the whole thing. So it has a whole lot of continuous pieces. Okay. So let's do a greatest integer function problem.
Oh.
We're going to graph this.
Okay.
So I've kind of made a modified t-table to graph this, and I'm just going to start at 0. So if I plug 0 into this, I get the greatest integer of half of 0 is 0 plus 1. And the greatest integer of 1 is 1. If I plug in a 1, I would have the greatest integer of half of 1. Half of 1 is a half plus 1,
No, still be 1.
and 1 plus a half is
1.5.
1.5, and the greatest integer of 1.5 is
Still 1.
1. And if I plug in a 2, I have the greatest integer of a half of 2
1
is 1
plus 1
plus 1, which is 2,
So
and the greatest integer of 2 is,
2.
okay. So what's happened here?
It's like repeating.
At 0, we had a y value of 1. And that y value of 1 stayed 1 until the moment it got to 2. And as soon as it got to 2, what's our y value? 2. Can you repeat that pattern? Or do we need to plot more numbers? It's going to stay there for about 2 units, and then it jumps up. And it'll stay there for about 2 units, and it's going to jump up. And so on. And we can go backwards. Open circle at the origin. Go back 2 units, close circle. Open circle, go back to close circle, and so on. We'll count to 6 pounds.
Yeah.
1,
2,
3,
3, 4,
4,
5, 7.
Okay, so there's the weight of the packages. And on the y-axis, yeah, I'm just going to kind of break it.
No.
And I'll say that 25 pounds is right there. Is that okay?
Yeah.
Okay. And then count by what?
3.
3.
Because it increases 3 pounds every, or $3 every pound, right? Okay. If I don't know a package, how much do I pay?
$0.
Do I graph that point? Do I graph the point 0, 0?
No.
Yes.
Oh, yeah.
You didn't do anything. There's nothing-
No.
You don't start there.
How many say yes, graph the point 0, 0? Hands up high. 1, 2, 3, 4, 5, 6, 7. 7 of you. How many say no, don't plot the point 0, 0?
I know there's a few with all
I
that
think-
memories.
Okay. How many of you cannot even count to 0? Okay. Look at what it tells me to graph. What am I graphing from and what am I graphing to?
0 to 6.
0,
0 to 6.
6.
Do I include 0?
Yes.
Wait, are we talking about 0?
Do I include 0?
Oh, JK.
No.
Yes or no?
I don't know.
I do not include 0 because this is an open interval. Do I include 6?
Yes.
Does that make sense? So would it be true that if I don't mail anything, it costs me nothing?
Yes.
But do I graph that point 0, 0? No, because that is not part of my domain. Okay? I have a specific domain that I'm graphing. I'm only graphing from just after 0 all the way to and including 6. Does that make sense? Pay attention to your domain. Okay. The second I mail something, and it's super, super light, how much does it cost me?
$25.
$25.
But I'm gonna have an open circle here, right?
Yeah.
And it's gonna stay $25 until
2
2.
pounds.
No, it should be equal.
and the instant I pass 2 pounds, how much is it gonna cost?
$20.
8.
But that's gonna be an open circle here, because the closed circle is included at 2. And how long is it gonna stay 28?
Till 3 pounds.
Till
3
till the other fraction of a pound.
Okay, notice these steps are different sizes, aren't they?
Yeah.
Okay,
Yeah.
0 to 2 pounds, that's 2 pounds worth. 2 to 3 is only 1 pound. So this run is wider than that run. And as soon as I get past 3 pounds, it costs how much?
31.
Okay. And can you see this pattern just going to continue? Do I include 6?
I do.
Yes.
Close circle, include 6. Okay, folks, that's what the graph would look like. What is the domain of my graph?
From 0. Infinity.
That's the domain, right? It's given to me. What is the range of my graph?
35
to 37.
25 to
37.
infinity with in parentheses?
Or it stops at
Well,
the
0.
domain can only go to 6. You can't. It doesn't-
Wait, are
ours
you
doesn't
using
keep
domain
going
or
up, so
range?
Yes,
it has to
I've
go
already asked for the domain. The domain's given. My question is, what's the range?
25 to 37.
25 to
25.
28, 31, 34, 37.
Yes.
What?
You cannot say that the range is 25
Oh,
to
because
37.
it
Oh, because it
stops.
includes- yeah.
Okay, because 26 is not included, is it?
No.
Is there a 26 Y value anywhere on that graph?
No.
No. Is there a 25.5 value anywhere on the graph?
No.
Is there a 25?
Yes.
28?
Yes.
31?
Yes.
34?
Yes.
37?
Yes.
That's the range. Okay? Based on the domain they provided, the range of this function is 25, 28, 31, 34, and 37. Good? Questions? I do not. And the last slide says the relation x equals y squared. Recall that a function is a relation where every domain is paired with one and only one range value. This relation, x equals y squared, is not a function. Using different y values, both positive and negative values, we find that connecting these points with a smooth curve, this is the graph of a parabola opening to the right with a vertex at 0, 0. So this part right here, what it's saying is, if I said that x is equal to 4 squared, what would x be?
8.
No. 16.
16. That would be the point 16, 4, correct? Because x is 16 and that's the y value, right? But if I chose a different point, let's say that x equals -4 squared, what's that give me?
Negative
16.
16,
16 -4.
which is the point 16, -4. Is it a function?
Yes.
It fails a vertical line test. The x value of 16 has two different y values of 4 and -4, right?
Yes.
That's why it's not a function. That's why it's called a relation. If I wanted to graph this, we're going to solve for y. So I have y squared equals x. Let's get y by itself. What do we do?
Square root.
Okay, and the square root of y squared is?
What?
Because I want to know. And the square root of x is?
What's for x?
Plus or minus the square
Oh,
root of x.
yes.
Because x is going to be a number. Okay? So if I was going to graph this relation, I actually have to break it up into two pieces. And if I was to enter y equals the square root of x into y1, and enter negative the square root of x into y2, that would allow me to see this relation. And there it is.
Wow.
Is the blue part only, if I ignore the red part, is the blue part only a function?
Yes.
Yeah, that's the graph of y equals the square root of x. What's the red one?
-4.
Negative square root of x, which it comes from the parent function square root of x, but that negative sign reflects it across the x-axis. Okay? So that's the only way you can graph this relation is to graph the two separate pieces. Questions?